So let's imagine that we're trying to accelerate an object faster than the speed of light. And remember that in Newtonian mechanics, there is no limit to speed. So as you are going to accelerate your velocity to infinity, what is also going to be accelerated is your momentum. And it's going to be very increasing until it's infinite. But also remember that a change in momentum is impulse. And in order to have an infinite momentum, you also need to have an infinite impulse. But this is impossible. You cannot have an infinite supply of force. It's simply just not logical. So Einstein hypothesized that there must be a speed limit. And this speed limit, he said, is the speed of light. Now, he didn't also only rely on this intuition, he proved it mathematically with the help of other scientists. I think one of them was called Minkowski. I have no idea, his name was weird. But what he did to modify the equation of momentum was include the relativistic factor, this one, which I think he called lambda. Now let's see how this relativistic factor changes from our Newtonian mechanics. So let's say that you have an object that is moving really close to the speed of light, and let's say it's moving at, let's say, 0.99 of the speed of light, 99% of the speed of light. So 1 minus, and this will approximately be 1, you're going to see that this denominator as a whole is approaching, all of this is going to approach 0. And it is a rule in mathematics, and you can visualize it, that as your denominator is approaching 0, this value over here, the value of the numerator, is going to be much greater. And as a result, your momentum is going to approach infinity. So as your denominator approaches 0, your momentum will approach infinity. What this tells us is that objects moving at very high velocities have such a tremendous amount of momentum that Newtonian mechanics, this equation over here, it does not take into account. Now, if you're talking about objects that, like, in our daily life, like me walking, my speed over here relative to the speed of light, is basically nothing. So the denominator will be approximately 1, and the Newtonian equation will hold true. But let's say, for example, you're talking in an atomic accelerator where electrons are being accelerated very close to the speed of light. Now, if we follow their path of the electron beam, and we're following in Newtonian mechanics, we expect as the electron is being deflected by the magnets, it is going to deflect at a steep angle. But this is not what happens, and this has been proven experimentally. What actually happens is that the electron beam barely deflects at all. It follows this path, the one in green. And why is that? It is because objects moving close to the speed of light, as Einstein predicted, have a great momentum. And objects with great momentum resist change to their path. They're not that easy to throw off their path. You can say, as our book said, they're stiff. So when you're talking near the speed of light, you need to include the relativistic factor into your calculations. And the universe does have a speed limit, and that is the speed of light. After developing his theory of relativity, Einstein set out to include gravity into his theory of relativity, and he struggled a lot to do that, until one day he imagined what he would go on to call the happiest thought of his life. Now, what was Einstein's happiest thought? It was a man falling from the roof of a building. And no, it was not the moment he hit the ground. His happiest thought was what the man was experiencing as he fell down from the roof of a building. As he fell down from the roof of a building, the man did not feel his weight. He felt weightless. And this can be proved because if there was anything that fell with the man, let's say his brush that he was cleaning the window with, it will fall at the same rate as the man. So in the man's perspective, this man's perspective over here, he nothing is moving. Earth is accelerating upwards towards him, and he is the one that is being stationary. Now recall from Einstein's first postulate that no motion is absolute. There is no reference frame I can call the right one. So I cannot say the man is wrong. The man is right. And if there is an accelerometer that fell with the man, it will measure no acceleration. So Einstein concluded that free fall has the same effect as no gravitational field at all. And this can be used to explain the fact why astronomers feel weightless in space. It's not because they're outside Earth's gravitational field, they are very much inside it. The reason why they feel that weightless is because they are falling around Earth with the spaceship and everything inside the spaceship. So to them, they are in an inertial reference frame. Now, this is what Einstein calls the weak equivalent principle. What is the strong equivalence principle? Imagine that you are in a spaceship, and let's draw it, deep into space where there is no gravity. Now you would be floating, and if you drop a ball, this ball will float as well. But what if the spaceship started accelerating upwards? What would happen is that the floor of the spaceship is going to press on your feet. The floor will accelerate upwards, so it's going to be here now. And it's going to press on your field, and you are going to feel as if there is a force of gravity, even though there is not. If you drop the ball in this case, the floor will accelerate up towards it, and the ball will hit the floor. So it will feel as if you are in a gravitational field. Guess what? If this spaceship accelerates at 9.8 upwards, it would feel as if you are dropping a ball on the surface of Earth. And this can be shown in this picture. So in this picture, he is like, I am on Earth because this rocket is accelerating. You can see the engines firing over here. And if you drop this ball, the floor will go up and it will hit it. So this is his equivalence principle. You cannot differentiate acceleration from gravity, and you cannot differentiate free fall from absolutely no gravity. Now, this can only be observed if you are in a small reference frame. What is meant by that is that the observation of this person is only true if he's talking about the spaceship. But if you are on Earth, Earth is so large that you are now capable of doing some physical tests that will prove to you that the effects you're seeing are of gravity and not acceleration. So Einstein was very careful when he said it. The equivalence principle is your inability to tell the difference between gravity and acceleration in a local region. Now, since gravity is not a force as Einstein thought by his equivalence principle, and since there is nothing in space to carry gravity, he realized, as smart as he is, that gravity is actually carried by space itself. And how is that even possible? What is gravity? Now, let's imagine that you have this two-dimensional plane, and this will resemble space-time. Let's think of it as space-time and recall from special relativity that Einstein united space and time into one thing called space-time. Let's imagine we have this straight fabric of space-time, and we place an object of very big mass. What would happen is the same as what would happen if you place a bowling ball on a trampoline, or if you place, let's say, some kind of metal on a sheet of cloth. It will bend downwards. And this is exactly what happens to space-time when there is a massive object like, let's say, the sun or Earth. The presence of mass will warp space-time around it. It will curve space-time, as you can see over here. Now, this is a two-dimensional representation just to make it easier to understand, but really this happens in 3 dimensions, but it's hard to visualize, so let's just imagine this in 2 dimensions. Now let's imagine an object. Was following a straight line through flat spacetime, and then it came around the curved spacetime because of this mass. What would happen is that the object will start to curve and follow spacetime as it curves around this mass. And this is gravity. Gravity is the result of mass warping spacetime about itself. So, if you look here carefully, you're going to realize that the distance from this point to this point is a line, but it's not straight. This line over here is called a geodesic. A geodesic is the shortest distance between 2 points on a curved surface. And you can think of it as being the same as what you would describe a straight line on 2-dimensional plane. So objects in orbit, or objects as they come about curved spacetime, they follow the path of a geodesic. And Einstein went even further, and he said that light, as it is passing through very massive objects, it will bend a little around it. It will follow a geodesic path. And this was against what Newton originally thought, because light had no mass. How then could gravity attract it if gravity is actually a force? But then scientists used the fact that light bends around massive objects to prove Einstein's theory of relativity. They actually did this. They measured the bending of light around massive objects. And this is gravity. In Einstein's world, it is very geometric. You can visualize it. And though Newton gave us mathematical formulas, Einstein gave us the physical visualization of how gravity actually acts. We now know enough to talk about free fall in relativity and in classical mechanics. Newton said that gravitational strength, and let's denote it by G, is equal to the force of gravity over a mass. And this mass over here is called inertial mass. Inertial mass is basically the measure of how difficult it is to change the velocity of an object. This mass is the property to resist acceleration. And we also know that the force of gravity Fg is equal to his famous equation, the universal equation, G multiplied by me, let's say this is the mass of Earth, multiplied by m over r squared. Now, the mass over here is the property of matter to attract objects. This is a measure of how much an object will attract another. We call this gravitational mass. Let's just say gravitational. So recall that Newton said all objects fall at the same rate, which is 9.8, regardless of their mass. And this was also proven by Galileo before him. The only way for this to happen is that when you substitute this value of Fg into g equals Fg over m, that those two masses cancel. So you have Fg, which is g me multiplied by m over r squared. All of this over m. The only way to have a constant acceleration or a constant g for here is for this mass, the inertial mass, to cancel with the gravitational mass, even though there is no reason it should be. Why is it that inertial mass is equal to gravitational mass? And Newton didn't really know why. No one really knew why. We just proved it experimentally. So Newton said that gravity is simply a force, and the greater gravity is a force that attracts all objects to fall with the same acceleration, 9.8. And since gravitational mass and inertial mass are equal, you can think of them as they cancel each other. So any increase in gravitational mass because the object got bigger would be cancelled out by an increase in gravitational mass. So it would always remain a constant, 9.8. But Einstein did not think this way, and he defined freefall in another way. How did Einstein define freefall? Now, we talked about the man falling from the roof of a building, and we said that he feels weightless. In other words, a man in free fall experiences the same effects as a man in space without any gravitational attraction. So Einstein concluded that a man in free fall, by his equivalence principle, does not have any forces acting on him. There is no force that is acting on this man. So he is in an inertial reference frame. An inertial reference frame is basically where you are stationary. And this is exactly what you would feel if, by some misfortune, you were to jump off a roof of a building. You will feel as if you are stationary and the earth is actually the thing that is accelerating upwards towards you. This is how you would feel. Again, by his equivalence principle, you're not wrong. Gravity has the same effects as acceleration. And another fact by which Newtonian and Einstein's definition of free fall differ is that Einstein said that free-falling objects follow a straight line downwards. But in Einstein's theory of general relativity, space-time itself is curved, so there is no such thing as a straight line. Instead, objects in free fall follow a geodesic, and recall that if I draw a sphere, the shortest distance between 2 points on the surface of the sphere is not going to be a straight line, it's going to be a curved line that we call a geodesic. And he said that all objects, they follow a geodesic. So the definition of free fall in Einstein's world is a person in an inertial reference frame following a geodesic. Now, in general relativity, the reason why all objects fall at the same rate is because free fall is not a property of mass. Free fall is actually a property of geometry. Let's think of it that way. The curvature of space-time close to the surface of Earth is basically the same everywhere. So all objects are going to follow the same curve, therefore the same geodesic. Because the curvature of space-time around the surface of Earth is the same steepness everywhere, so no object is going to fall down quicker than another object close to the surface of Earth. They're all going to fall through a similar geodesic, therefore the same acceleration. It is a property of the curvature of space-time and not a property of mass, size, or composition of matter. So here is a general comparison of free fall between Newton and Einstein. While Newton said that a free fall experiences only gravity, Einstein realized that the person that is falling will not experience his weight at all. He will experience weightlessness. So it is equivalent to having no force acting on him. You are in an inertial reference frame when you are weightless. Right now you feel your weight. So according to Einstein, you're not in an inertial frame of reference. So it is acted by no force and it follows an inertial reference frame. And while Newton said that a free-falling object falls down in a straight line perpendicular to Earth, Einstein realized that space-time is actually curved, and objects follow a geodesic, so you will fall down like this. Because space-time itself is curved, you cannot follow a straight line through a curved surface. And Newton realized that inertial mass is equal to gravitational mass, but did not give any explanation for that. The simplest way to explain constant acceleration, g being a constant, in general relativity is to think of it geometrically, because the steepness of the curvature of spacetime around Earth is going to be the same, approximately the same everywhere on Earth, around the surface of Earth. So all objects will follow a similar geodesic down. So therefore, it is constant acceleration. They're basically two very different ideas. And free fall is one of the major topics in which classical physics differs from general relativity.